Hi, everybody. This is your examples video for translations and reflections and rotations. So I am working in the rigid motion transformation notes document. I'm going to go through and do these columns here that you can see on the screen on the right. So I'm going to do these example columns for you. If you haven't seen the previous video, make sure you go back and watch that because I talk you through all of this function notation and vector notation. Okay. After this video, I do have 3 other videos that deal with practice problems, maybe that are a little bit different than these examples, that deal more with like shapes and they're a little bit more detailed and in depth. So there's one for each type of transformation. So translation, reflection, and rotation, right? So let's go ahead and jump into it here, okay? So if you remember, a translation is a shift, okay? And they're telling me how many units I'm moving left or right and how many units I'm moving up or down, okay? So here, right? If I wanted to write this as a function, so I'm taking this coordinate point and I'm moving it 3 units to the left and 5 units down. So my function here is x comma y. It always starts with x comma y. That's your input, an arrow, and then you have to write your output, which is x plus or minus a number, comma, y plus or minus a number. Okay, and here, that's where this description comes in. So I'm moving 3 units to the left. Okay, left is negative for x. So I would say x minus 3 here. Okay, and then down is also negative, right? It's negative for y, so I would do y minus 5. Okay, so what this helps us do now is I can say, okay, now my coordinate point is xy. So wherever I see an x, I'm going to plug in an 8. And wherever I see a y, I'm going to plug in -9. Okay, so here I have 8 -9 becomes something else. So you have 8 minus 3 here, comma, and then -9 minus 5. Okay. So the input is going to stay the same. You're not doing anything with the input, okay? And then you have to do this subtraction right here. So I have 8 minus 3, which is 5, and then -9 minus 5, right? They have the same sign, so I'm going to add the numbers and keep the sign. So 9 plus 5 is 14, and then I'm going to keep my negative sign. So what this means is that the point 8, -9 became the point 5, -14, okay? It's very, very similar with vector notation. It's just you don't have this function out. Okay, so with vector notation, I have my capital T right here, which means translate. Okay, this number right here is how far you're moving for X, and this number here is how far you're moving for Y. Okay, so, and then this is your input. That's like your original coordinate point. Okay, so with vector notation, I know I'm going to add 2, because this is a positive number, add 2 to x, and then I'm going to add 7 to y. So I have -6, 1 becomes -6 plus 2, comma, 1 plus 7. Okay, so -6, 1 becomes -6 plus 2 is -4, and 1 plus 7 is 8. Okay. So translations are pretty simple. You're literally just adding or subtracting however many units are given to you in the actual problem. Okay. All right, so give me a second to clear my screen off, and then we're going to talk about reflections. Okay, y'all, so let's do some examples with reflections next. Okay, so reflections will have different rules depending on which reflection you are doing. Okay, so I'm going to talk about the main 4 that we see more often than anything else. Okay, so those main 4 are a reflection over the x-axis, a reflection over the y-axis, a reflection over the line y equals x, and then I'll scroll down and do a reflection over the line y equals negative x. Okay, so the rule for reflection over the x-axis is you change the sign of your y value, which I'm hoping kind of intuitively makes sense, right? If you have a shape, right, and you reflect it over the x-axis, all the original y values, which were positive, are now negative, right? And the x values didn't change at all. I didn't move it left or right, okay? So all you have to do is change the sign of your y value. So here, for my function notation, I have 8, -9. My y value is -9, so that's the one I'm going to change the sign of. So I have 8, 9. It's really that simple, okay? For the vector notation, you see you have the lowercase r, and then it says I'm reflecting over the x-axis, so I just have to remember that x-axis means I'm changing the sign of my y value, okay? So I have -6, comma, my original y value was 1, so my new y value is -1, okay? Next comes a reflection over the y-axis, which is exactly the opposite of what we just did here. Okay, I'm going to take my original point and I'm only going to change the sign of the x value. Okay, which again, I'm hoping kind of intuitively makes sense. Okay, if I have, say, like a half circle, right, and I'm flipping it here over the y-axis, right? It's going to flip it and kind of turn it around and make it backwards, right? My y value hasn't changed at all. It hasn't gone up or down, but all my x values, which originally were positive over on the right-hand side, are now negative, right? They've changed their sign, okay? So if I'm going to reflect this point, 8, -9 over the y-axis, I just know I only have to change the sign of my x value. So 8 becomes -8, and then my 9 is still -9, okay? Same thing for the vector notation. It says a reflection over the y-axis, so if my original point is -6, 1, I know all I have to do is change the sign of my x value. So -6 becomes +6, and 1 stays the same. Okay, let me scroll just a little bit here, so that we can talk about these other things, okay? So a reflection over the line y equals x. The line y equals x looks like this, okay? Like, so it literally just goes straight through on a diagonal, okay? The rule for a reflection over the line y equals x is you just switch your x and your y values. You're literally just swapping them, swapping their order, okay? So here, if I'm reflecting this point, 8, -9, over the line y equals x, all I have to do is switch my x and my y. So instead of 8, -9, it's 9, a -9. Oops, hold on. I accidentally wrote a negative sign there. Don't want a negative sign. Okay, so I'm just going to switch these. So 8, -9 becomes -9, 8. Okay, same thing for the vector notation. You see a lowercase r, so that means reflection, over the line y equals x. So I'm just going to switch my x and my y. So -6, 1 becomes 1, -6. That's it, okay? Then my last one here is a reflection over the line y equals -x. So it's the same kind of thing as the one that we just did, y equals x. It's just this time it's the same slope, right? It's like a slope of 1, but it's negative this time, okay? So we have two things that we have to do when we are reflecting over this line, the line y equals -x. You have to switch your original x and y values, but you also have to change their signs. Okay, so swap and change sign. Okay, all right, so if I have my point 8, -9, I'm going to switch those. Okay, so I have -9, 8, but then I need to change their signs as well. So -9 becomes +9, and +8 becomes -8. Right? And then it's the exact same thing when you see it in vector notation. Right? So I'm reflecting over the line y equals -x. So I have -6, 1. I'm going to switch their order. So 1, -6, and then I need to change the sign of both. So 1 becomes -1, and -6 becomes +6, right? So that's the bulk of the reflections that have a function or like a rule that you can always follow that will always work. Um, Sometimes if you're given a picture where the line of reflection is like a weird line, like y equals 4 or y equals -2x plus 3 or something like that, you kind of just have to do it visually and count uh, along and make sure that the distances between the mirror and the shape is the same on both sides, like on both sides of the mirror with both the pre-image and the image. Okay, so give me 1 second to clear my screen off and then we're gonna talk about rotations next. All right, y'all, so this is the last part of this video where I'm going to do some examples with rotations for you, okay? Um, just like reflections, there's an infinite number of possible rotations, right? You can rotate things anywhere from 0 to 360 degrees. And then you can rotate them around the origin or just about any other point that you can think of, right? But there's 3 that are really, really common that we actually have functions for and things that will work every single time, okay? So those are rotating 90 degrees counterclockwise, rotating 90 degrees clockwise, and then rotating 180 degrees. Okay, so I'm going to talk about those 3 things. Okay, so the function for rotating 90 degrees counterclockwise, so remember, counterclockwise is going this way. Okay, it's the opposite direction that a clock goes. Okay, so the rule is that you switch your x and your y values, and then you change the sign of your new x value. So the first coordinate uh, in your new coordinate point. Okay, so the new x value, old y value. Okay. Um, Notice here that this 90 degrees is positive. Okay. Positive means that I'm rotating counterclockwise. Positive is counterclockwise, okay, which is kind of the opposite of what you would normally think. Okay, but if you see a positive rotation, then that means you're going counterclockwise. Okay, right? And then here I'm rotating around the origin. If this, so the origin, remember, is the right? It's the point where the x and y axes meet. Okay, these functions don't work if you move the point of rotation, right? So I can take this triangle and rotate it 90 degrees this way, right? And I can actually track those points. But if I go and I move this point, say, down here, okay, you kind of have to draw the actual circle in, which you'll see when I do some practice problems for you with these rotations. But you kind of have to draw like a little line to the point that you're trying to rotate. And then if I'm rotating it 90 degrees, I would draw another line that's the same distance, right? The same length that was 90 degrees counterclockwise going this way, like I'm making a 90-degree angle right here, and then I would take my shape and rotate it kind of like that. So see how it's like pointed in the same direction, but it's in a much different location, right? So all that to say, this rule only works when you are dealing with This rule only works when you're dealing with rotating about the origin, okay? So here's my coordinate point, 8, -9, and I'm rotating positive 90 degrees around the origin. Okay, so I'm going to switch my x and my y, so this becomes -9, 8, and then I have to change the sign of just the first new coordinate here. So -9 becomes +9, okay? Then it's the exact same thing with the vector notation. Notice that my vector notation is a capital R this time, which means rotate. Okay, and I'm rotating around the origin and I'm rotating 90 degrees. Okay, so I have -6, 1 becomes, I'm going to switch my x and my y. So 1, -6. Then I need to change the sign of my first coordinate point here in my new point. So 1 becomes -1. Okay. I'm hoping that you can kind of see what's actually happening here, and why this kind of makes sense. So the original point, 8, -9, is way down here in quadrant 4, and the new point, 9, 8, is up here, right, in quadrant 1. So that's your 90-degree counterclockwise rotation. Same thing for this one, right? The original point, -6, 1, is right here, and the new point, -1, -6, is down here, right? Taking this and rotating that point 90 degrees counterclockwise, okay? All right, next is a rotation 90 degrees clockwise around the origin, okay? Notice that we have a lot of similar things going on here. So the rule is I'm switching my original x and y values, but this time instead of changing the sign of my new x coordinate, like my first coordinate, I'm changing the sign of my new y coordinate, my second coordinate in my new point, okay? And notice again that you have a negative sign here in front of the 90. Negative angles means clockwise, okay? Always and forever till the end of time, okay? So if my original point is 8, -9, I'm still going to switch my x and y values, -9, 8. And then I'm going to change the sign of my second coordinate. So this becomes -9, -8. Okay. Same thing with the vector notation. I have -6, 1. I'm going to swap my x and my y. So 1, -6. And this time I'm going to change the sign of my second coordinate point. Right. So this is 1, 6. Right. If there's a plus sign right here, you can kind of like you can just eliminate it, right? Like you can get rid of the plus sign. It's implied. Okay. All right, and then my very last one is a rotation 180 degrees around the origin. This one's very, very simple. No swapping. You just have to change the sign of both of your coordinate points. So just change the sign of both. No swapping. Okay. So if my original point is 8, -9, I'm just going to change the sign of both of those. So 8 becomes -8, -9 becomes +9. Okay. Same thing in the vector notation. If my original point is -6, 1, I'm just going to change the sign of both of those. So -6 becomes +6 and 1 becomes -1. All right. So these are the most common types of questions that show up with translations, reflections, and rotations if you're not given a picture to play around with, right? Where you can actually draw the translation or the reflection and the rotation and kind of track where the points go. Okay. So my best advice to you all is I would do your best to memorize as many of these as you can. Not for my class specifically, because I think that it's silly that we ask you to memorize trivial things like this. It's more important to me that you actually know how to do the process, not that you know, like that you can remember off the top of your head that to rotate 180 degrees around the origin, you change the sign of your x and y coordinates. Okay? But on like standardized tests and things like that, these are really like the SAT, the ACT, the like state tests, things like that. These are very common types of questions that if you remember how to, like you remember some of these rules, it'll make doing those questions a little easier. You'll be able to do it a little bit faster, right? But for me, I will always give you these functions, especially. I'm not going to make you memorize them. Right. So in the next video, I'm going to do some different types of practice problems where we're going to have some more visuals, some more tables, and things to play around with. So I will see you in the next video. Bye, everybody.